Alright folks, today we're going to take a little bit of a foray away from traditional programming. We're going to talk about basically how a computer works. And the first thing you ought to know is how computers think. So whenever you tell it to do something, like add two numbers or find a function, what is it really doing? Well, it needs a brain, and its brain is built a little bit like ours, but much simpler. This is the brain of a computer, essentially. This is a very small part. This is two transistors, which are essentially like neurons. Um, these guys right here, sorry, there's a plane overhead. These guys right here take an input from A and then control their output right here. So they can take an input A and B and they control what goes to the output. So if they're adding two numbers, they might take A and B. They take a signal and turn these on or off and put them together. This is a lot like a neuron. We can see here that the neuron has a dendrite that connects to its cell body, and then the output goes out the axon. So they're very, very, very similar, except human dendrites can have many, many inputs and many, many outputs, which makes us better at handling things like recognizing faces and emotions and thinking like that. Whereas this, having a singular input and a somewhat singular output, makes them really good at dealing with numbers. And that's what computers are good at. This right here, you can imagine being strung together to come up with a very, very fancy way of thinking about numbers. Most modern processors have billions of transistors, whereas you're only looking at two. So you can imagine the fancy things you could do with a billion of these. So let me show you how this fundamentally works. So computers can't think in emotions or feelings or ideas like we do. They think in numbers. And this is how they think. So I'm going to fill this table back in here in a second, but they can only think in binary because their inputs are either on or off. If you have electrical current here, the computer thinks of that as a 1. If you don't have electrical current here, the computer thinks of that as a 0. So there's only really two things a computer can think about, whether it's on or whether it's off. So all the number systems have to really be represented by either on or off. Which is a binary base 2 system. Whereas we use numbers that are a base 10 system because we have 10 fingers, I think. And so here's the comparison. A 0 in base 10 is a 0, and the same as base 2. A 1 is a 1. A 2 looks like a 10, but you can't think of it this way. You have to think of it as this is the 2's place, and this is the 1's place, okay, or the nothing's place, I guess. A 3 is a 3. And a 3 in base 2 looks like an 11. But again, you have to think of it differently. This is the 1's place, so we have 1, 1, and this is the 2's place. Well, we have 1, 2, and 1, 1, we have 3. We then run out of digits, so we need to add a third digit here to make a 4. And you can see here we have no 1's, no 2's, but a 4. So this is the 4's place. You can think of this as analogous to how we think of base 10 numbers. Base 10 numbers, we could write a number like 1,205, or 125, excuse me. Let's just go with my original one, actually. 1,250. Well, you know what each of these numbers means. This is the thousands place, because we're thinking in tens. So we have, how many groups of 10 make 1,000? Well, 3. Okay, so you have 1,000. Now you have in the hundreds place. Well, how many hundreds do you have? You have 2. So you know you have 1,000 plus 200. Now how many tens do you have? Well, you have 5 tens. So you have a 50. You add a 50 onto that. How many ones do you have? None. This is the exact same thought as in binary, except we think of everything in multiples of 2. If we go down to the number 5, you can see here that it has a single 1, no 2's, and 1 4. So the 4's place is a 1, so add 4 and 1, and you get 5. You can see here 6 is the same way. You've got 1 4 and 1 2. 7 is the same way. You've got 1 4, 1 2, which makes 6, and add another one. And then we run out, so there's no digits left. We can't write the number 2, just like you can't write the number 10 with one number. It's impossible. There is no single character that means the number 10. So if we do here with the number 8, we have to add a new space. So that's the 8's place. So we have 1 8, which represents the number 8. So 1 0 0 0 is the number 8. Finally, moving down to 9, we have the exact same situation, except we add a singular one. The number 10 is very similar, but all we have to do is add a number, an 8, skip the 6's, or the 4's, excuse me, and then add a 2. because 8 plus 2 is 10. So let's check this. Let's do a math problem here. Let's do 3 plus 4, okay, which we all know equals 7. But in binary, this is 1, 1 plus 4, which is 1, 0, 0. Does this work out? We end up with add the fours places, you get a 1. Add the twos places, you get a 1. And add the ones places, you get a 1. And we can see here that in binary, 1, 1, 1 is indeed 7. This is how computers add. They can add just like you, but they think of the numbers in a completely different way. So this is the first lesson in computer anatomy. This is how computers think.